Welcome back to Module 13 of Com 3073, Conducting Communication Inquiry. In the past few weeks, we talked about various quantitative research methods, including experiments and surveys. Remember that the overarching goals of these methods is to collect quantitative data on different variables in our hypotheses and/or research questions. The next step after we collect these data is that we must analyze them and see whether the patterns we uncover support or fail to support what we hypothesized or asked about. The following series of videos will gently ease you into the sometimes scary world of statistics. You need to know about statistics because it reflects the set of tools you'll need to determine whether the data in front of you supports what you guessed. I know you probably want to crawl under your sheets in your bed right now, but my hope is that this will be an understandable and gentle introduction into these basic statistics. So let's get into the world of statistics. The most logical starting point to discussing statistics is to, of course, define what I mean by statistics. Statistics is in itself a scientific discipline, and it's studied in departments all across our nation and world in much the same way communication, psychology, anthropology, and mathematics are studied. As I mentioned on the first day of class, I got a PhD minor in statistics, and I struggled every day through those upper level courses. When I use the term statistics, I'm actually referring to an entire process of collecting, organizing, and interpreting data taken from a quantitative study, such as the survey method, experiments, meta-analyses, and quantitative content analyses. You may have noticed that I use the term process to define statistics, and this is important because it's indeed comprised of sequential steps in a process. In the first step, you have to organize your data in a way that makes sense to you. We usually array our data in a spreadsheet like the ones you find in Microsoft Excel, where each row represents a person or case, and each column represents that person or case's response to a single item. In the second step, you must summarize your data. This means you have to take a large amount of quantitative data and synthesize it or pare it down to numbers that are easily understandable, often using means or standard deviations. These numbers give you an idea of the patterns that exist among the variables. In the third step, you draw conclusions about whether the summary statistics support or fail to support your hypotheses. Note that I didn't use the words proved or disproved in relation to statistics because, as I mentioned in a prior slide, we are never able to prove anything through research in a falsificationism world. The final step is to make your results available to the public in written or oral form. For researchers like me, this involves presenting my research at academic conferences or writing up my results for publication in a peer-reviewed journal. There are two major families or classes of statistics. The first is called descriptive statistics, and these summary data are used merely to describe the characteristics of your sample and nothing more. Common descriptive statistics include sex composition, that is, the percent of males and females in your sample, the average age of your sample, and ethnic makeup of your sample. These are all considered descriptive statistics because they're describing your sample. In almost all of my studies, I simply want to report to the people reading my research that my sample consisted of, say, 25% males and 75% females. I'm of course not arguing that this is the sex breakdown in the population, so this would be considered a descriptive statistic. The second is called inferential statistic. Here you may be using summary data like correlations, t-tests, and ANOVAs to infer or propose what's happening at the population level. These statistics are our best guess of whether a proposed relationship exists or does not exist at the population level. One note of importance that is reviewed from a previous video: statistics are summary data at the sample level, and parameters are theoretical summary data at the population level. Why do you think I say theoretical? You might have already guessed that we usually can never know this number because we almost never have access to all observations in the population. Let's take a step back and get a 10,000-foot view of the steps that happen in a research project and where descriptive and inferential statistics might find its place. Let's say I'm interested in the effects of smartphone use on the academic achievement of college students. I do a lot of research looking at past studies on smartphones' effects on a broad range of different achievement variables, and I come to the best guess or hypothesis that among college students, the time they spend on smartphones is negatively associated with their cumulative GPA. I then embark on my research project. I start by convenient sampling undergraduate students from different departments at UTSA, and I collect a couple of hundred people in my sample. Using the survey method, I ask these students to complete a simple questionnaire at one cross-section of time. In the questionnaire, I ask students basic demographic questions like their age, sex, and ethnicity, and I ask them to estimate the time they spend using their smartphones per day and their cumulative GPA. I input all of the questionnaire results into a Microsoft Excel file and compute statistics of interest to me. In the write-up, I describe my ethnically diverse sample I collected by saying that the sample consisted of 54% Hispanic Latinx, 23% white Caucasian, and so on people. Because I computed these percentages for the sole purpose of telling the readers, here's the kind of people the data were taken from, these are considered to be descriptive statistics. Later in the report, I write, the correlation between time on smartphones and cumulative GPA was significant, with an R that's equal to 0.25. The R that's equal to 0.25 indicates to the reader the strength and direction, whether it's positive or negative, of that correlation. The correlation of 0.25 was computed with data taken from the sample, so this means that the R value is a statistic. But the R statistic is trying to make a faithful effort to estimate the population correlation. In this case, the best possible guess we have about the population correlation is what we found from the sample level. So in this case, we would guess that the population correlation is also 0.25. By the way, the population correlation looks like it's represented by a P. That's actually not a P. That's the Greek alphabet rho. And it again represents a correlation at the population level. Because it's a population level estimate and not a sample level estimate, we call rho a parameter, not a statistic. Also, because R, the sample level statistic, is trying to make inferences about rho, the population level parameter, we call R an inferential statistic. Next, we're going to focus our energies on how to pare down your data into workable parts. Remember that when you input all of your data from your hundreds of participants into a spreadsheet, it'll be difficult to see patterns among the variables. So we need a way to synthesize the data into smaller components. This is where measures of central tendency help us. A measure of central tendency is a single value that attempts to describe a set of data by identifying the central position within that data. The most common measures of central tendency, which you might remember from middle school math class, are the mean, median, and mode. The mean or average is by far the most commonly used measure of central tendency in social scientific research because it reduces data without losing any real information. You of course compute an average by summing all scores and dividing the sum by the number of scores you summed. The median is sometimes reported as descriptive data when there are a few large scores called outliers that are skewing the results. The median is found by arranging all the scores in your variable and taking the middlemost number. If there are two middle numbers, as will happen in a variable with even numbers of scores, you average the middle two most numbers. The mode is the most frequently occurring score in your variable. I honestly have used the mode function only once, and it was to determine what the most commonly used strategy to prevent cyberstalking was when each strategy was represented by an arbitrary number. Let's dive a little deeper into the measures of central tendency by looking at some of their equations. Recall that the first measure of central tendency is the mean or average, which is represented by the following equations. For a sample mean, called x bar, you have to sum or add, represented by the Greek alphabet sigma, each individual score, represented by x, or sometimes x subscript I, and divide that sum by the total number of observations or scores, represented here by a lowercase n. The equation for x bar is exactly the same as the population average, except you're summing scores for every single object or element in the population and dividing it by the total number of members or objects in that population. As a side note, the population average is called mu, not mu. Here's a quick example of how we can use the mean in a research project. For use as descriptive data in our report, suppose we wanted to know the mean number of hours per day college students read online or paper newspapers. We asked 10 college students to respond to the question, how many hours per day do you spend reading online or paper newspapers? Here's our data set. You can see from this data set that the first college student responded that he or she spent about 3 hours per day reading the newspaper. The second college student spent about 5 hours, and so on. Now let's apply the x bar formula. You recall that the sigma x part tells us to sum or add all the scores in our data set, and then you divide that sum by the total number of scores, which in this case is 10 for the 10 college students who responded to this question. X bar, if you add up all of these numbers and divide it properly, is equal to 3.9. The interpretation here is that the average time per day college students in your sample spent reading the newspaper was 3.9 hours, and this is exactly how you would write it up in your research report. You'd probably include standard deviation too, which we'll get to later in this video. The next measure of central tendency we're going to focus on is the median. Remember that in looking for the central value, the median is essentially the middlemost number in a series of scores. To find this middle number, you have to take two easy steps. First, you arrange all the scores in order from smallest all the way to the largest value. Next, you find the midpoint value in that series. Here's the newspaper reading data set we looked at earlier. If we arrange all the data from smallest all the way to largest, cross out all of the outer scores, we find that the midpoint numbers are 3 and 4. In this case, because there's no true single midpoint, we average these numbers to get 3.5. Our interpretation is therefore that the median time per day college students in our sample spent reading the newspaper was 3.5 hours. And this is exactly how you would write it up in the research report. The final measure of tendency we'll look at is the mode. The mode again is the most frequently occurring number in our data set. It's pretty easy to identify the mode, and remember sometimes you can have more than one mode per data set. To find the mode, you must follow two steps. First, like in the median, you need to organize your data from the smallest value all the way up to the largest value to make things easier on you. Second, You identify which numbers in the dataset occur most frequently. Let's go back one last time to our newspaper consumption dataset. Like I said before, you first sort your data in the first step, from smallest value all the way up to the largest value, and then you see which numbers appear most frequently. In this case, 2, 3, and 5 are represented twice, whereas all other numbers appear only once. What does this mean? This means that the mode hours per day that the college students in your sample spent reading the newspaper was 2, 3, and 5 hours. Variability or dispersion answers the question of how far in distance the individual scores are away from the mean or average. In other words, variability addresses the quantitative spread of the scores on a particular variable. The range is by far the simplest measure of variability. The range is found by taking the largest score and subtracting it from the smallest score in a dataset. Range is most commonly used as a marker of dispersion for age. Variance and standard deviation are very similar in that they give you a summarized number of the spread of scores away from your mean. For variance, that number is unstandardized, making its interpretation sometimes difficult. For standard deviation, the value is standardized, making it easier for us to interpret. Here's a quick example of range. Suppose we had a sample of 10 individuals and we wanted to know the dispersion or variability of ages for the sample. We therefore sought out to find the range of these ages. Here's the data set of ages in our sample. You'll notice that I sequentially sorted the ages to help us through this process. You can see that the ages for our participants range from 18 all the way up to 64. Recall the definition of range that I just mentioned. Range is calculated simply by taking the largest value, which in this data set is 64, and subtracting it from the smallest value, which here is 18. Therefore, the range in this example is 46. The interpretation here is that the average age of the sample was 42.1 years old with a range of 46 years. You can see here that the range gives us a very basic idea of how spread out the ages are across our dataset. One word of caution. The range is heavily influenced by extreme scores in a dataset compared to other metrics of dispersion or variability. As an extreme example, if you have 100 18-year-olds in your dataset and just one 100-year-old person in your sample, the dispersion of ages would in reality be really small, but the range would still be 100 minus 18, which equals 82, which is quite a large variability. Here's a visual illustration of variance to get us started. Do you remember how I defined variance earlier? I said that variance was the unstandardized summary value of the spread of data points or scores from the mean, which in this example is 78. To visualize this, suppose you had two different samples, a green group and a purple group. Here's the spread of each individual score on a variable, say a measure of love for one's romantic partner. In this case, which group would you say has the higher variability? If you said the green group scores would have higher variability, you'd be absolutely right, because the individual scores are spread out more from the mean. Here are the equations for variance at the sample level and the population level. It looks a little complicated, but you already know all the moving parts from the mean equation. Variance for a sample, represented here as S squared, is equal to the sum of each individual score minus the mean, then squared and divided by the total number of observations minus 1. Don't forget when calculating variance that you must follow the correct order of operations. You might remember the acronym PEMDAS or the mnemonic "Please excuse my dear Aunt Sally" for help on identifying the correct hierarchy. Variance for a population, which is represented by the lower sigma square, is exactly the same equation as the sample variance, but the denominator is just n rather than n minus 1. N minus 1 is used in the sample variance to make it an unbiased estimator. The reason why n minus 1 becomes an unbiased estimator, whereas n would be a biased estimator for the sample variance, is beyond the scope of this class. If I told you that variance was represented by s squared, and standard deviation was represented by just s, how would you find standard deviation? Well, to get s from s squared, you have to square root s squared, and you would have to do the same for both sides. Therefore, standard deviation, represented again by s, is equal to the square root of your variance. Here is an example of how we would calculate variance and standard deviation of a small sample. Suppose we wanted to know the variance and standard deviation of scores on a relational regression measure for a small sample of children of recently divorced parents. The n here represents total sample size, which in this case is 3 for the 3 children we recruited. The first step is to find the mean. Remember that the mean or average is found by summing each individual score and dividing it by the number of scores we summed. So in this case, we would take 1 plus 4 plus 7, which is equal to 12, and divide that by 3 because there are 3 children's scores, which gives us 4. So the average relational regression score for the children in our sample is 4.0. But we still know nothing about variability. The next step, according to the equation, is to take each individual score and subtract it from the mean. So for Gary, his score was 1 and the group mean was 4, so the component inside the parentheses for Gary is -3. For Anne, her score was 4 minus the group mean of 4, which is equal to 0. For Mark, the component inside the parentheses would be +3. You then square these differences. So for Gary, -3 squared is equal to 9. For Anne, it would be 0, and Mark would be 9. You add all of these products up to get 9 plus 0 plus 9, which is equal to 18. This 18 represents the top or numerator of the variance equation. All you need is the bottom or denominator of the variance equation, which is equal to total sample size minus 1. Because there are only 3 people in your sample, the denominator would be 3 minus 1, which is equal to 2. If you divide 18 by 2, you get 9, which is your variance. To compute the final standard deviation, you would need to square root both sides, giving you the final product S, or standard deviation, which is equal to 3. In your write-up, you would probably write something like, the mean aggression scores for the sample of children of recently divorced parents was 4.0, and in parentheses, variance equals 9.0, and standard deviation equals 3.0. You may have heard of the term standard deviation and seen it applied to different values like age or even test scores. A standard deviation is a unit of measurement on its own and has meaning. If your scores on a variable were hypothetically arranged like a perfect bell curve, it means that 68.26% of your scores fall within plus or minus 1 standard deviation unit from the mean. This also means that 95.44% of the scores fall within plus or minus 2 standard deviations from the mean. An important number you should commit to memory is 1.96, and you'll see it come up time and time again in the future. This number in standard deviation units is meaningful because it means that 95% of the sample falls within plus or minus 1.96 standard deviation units from the mean. So let's take a look at how you would interpret standard deviation after you calculate it. Suppose you surveyed exactly 100 people and you were interested in people's attitudes towards the current Congress. You used the one-item measure that asked people to estimate their evaluations of Congress's performance on a scale from 1, which is very negative, all the way to 10, which is very positive. After you computed the data, you found that the mean of the attitudes was 4.2, just a little bit below the midpoint, with a standard deviation of 1.3. So what does this mean? It means that one standard deviation unit is equal to 1.3. As I mentioned previously, one standard deviation unit is equal to about 68% of the sample's scores. So what do you think 2 standard deviation units is equal to? If you said 2.6, you'd be absolutely right. Now, how did I get 2.6? I merely multiplied both sides by 2. So 2 times 1.3 is equal to 2.6. Likewise, if you wanted to calculate 3 standard deviation units, you'd multiply 1.3 by 3. So what does this mean in the grand scheme of things? It means that about 68% of your sample scored within plus or minus 1.3 points around the mean of 4.2, and it also means that about 95% of your sample's attitudes towards Congress was about plus or minus 2.6 points around your mean of 4.2. In other words, 95% of the ratings on Congress of your sample fell between 1.6 points and 6.8 points, assuming that the distribution was normal. Let's quickly try one more example because this idea of standard deviation is really important. What if I told you that we hypothetically had a cumulative exam at the end of the semester, by the way, which we don't, and I told you that the mean score on this exam was 80% with a standard deviation of 2.5%? What should that automatically tell you if you knew the scores on the exam were normally distributed or looked like a bell curve? First, you should observe that one standard deviation unit is equal to 2.5%, which should also tell you that 2 standard deviation units is equal to 5.0%. And of course, you get this simply by multiplying 2.5% by 2. This tells you that about 95% of the class scored between plus or minus 5% from the mean of 80%. In other words, approximately 95% of the class scored between 75% and 85%. That's pretty much all I have for Module 13. Thanks for sticking with me through this video and not automatically closing your browser once I said Introduction to Statistics. My guess is that you're a little more at ease after watching this video, but of course you can email me if I'm dead wrong and we can chat about any of the concepts I covered in greater detail. We covered a good amount of information in today's video. Today I defined what statistics are and how they relate to parameters. I discussed the differences between descriptive statistics and inferential statistics and when it's appropriate to use either. I then talked about measures of central tendency and showed you how to find the mean, median, and mode in a dataset. We moved on to measures of variability where we computed by hand variance and standard deviation. By the way, if you found calculating standard deviation to be easy, that's pretty much how difficult the rest of the statistics we're calculating in this class will be. So I hope that somewhat eases your anxiety. As always, please let me know if you have any questions about the readings or content in this video. Please don't forget about reading the textbook pages listed in the syllabus, and don't forget about this module's quiz. Have a great remainder of your week if I don't hear from you. Peace out.